Okay everyone, so this is now the last lecture of the course, and today we're going to cover the fundamental theorem of Galois theory. Okay, so here's the setup. We let K over F be a Galois extension. Then Galois theory is primarily about the relationship between this field extension and the Galois group, which is the group of automorphisms of K fixing F. And now note that to any subgroup of the Galois group, we can associate a field, namely the fixed field. So we let KH in K be defined as the fixed field of H. And note that this field always contains F because every element in the Galois group fixes F, so the fixed field has to contain F. So we always have that KH is in between F and K. The fixed field of H is always in between F and K. So we call this an intermediary field. So since it lies in between F and K, we call this an intermediary subfield. Between F and K. Okay, so we have a correspondence that associates to every subgroup an intermediary field. So this defines a map between the set of subgroups of the Galois group and intermediary fields between F and K, where we take a subgroup H to the fixed field. Okay, and the fundamental theorem of Galois theory tells you that this gives us a perfect, a one-to-one bijective correspondence. So in effect, we can completely turn the field theory of fields between F and K into a study of subgroups. Okay, so the theorem fundamental theorem of Galois theory let's call this correspondence, let's call this map phi. So the map phi subgroups of the Galois group mapping to intermediary fields given by taking, sorry, this should be F. Given, so I should say, sorry, K over F, Galois extension. Then the map taking a subgroup H to the fixed field KH is bijective. So it gives us a one-to-one correspondence between subgroups of the Galois group of some Galois extension and intermediary fields. Furthermore, this correspondence is inclusion reversing. Meaning that if H1 is a subgroup of H2, then KH2 is a subfield of KH1. So smaller groups give bigger fields. Okay, let's prove it. Okay, so we've actually proven already that so we've already proven in prior lectures that this correspondence is injective. Namely, we proved it when we proved the following proposition, which I've just taken directly from the previous lectures. Okay, so we had the following proposition. We said that if K was a field and G1, G2 were two subgroups of the group of automorphisms, then the fixed fields are distinct. So we said that if K was a field, G1 and G2 are distinct subgroups, then the fixed field, so then if F1 is a fixed field of G1, F2 is a fixed field of G2, then F1 and F2 are distinct. So we've already proven that given distinct subgroups of the automorphism group, the fixed fields are distinct. And so, in particular, if we apply this here, then if we take two distinct subgroups of the Galois group, then the fixed fields will be distinct, so phi is injective. Okay. So it remains to prove surjectivity of phi. Okay, so take some intermediary subfield, L. So take some intermediary subfield L. So we know that every Galois extension arises as the splitting field of some polynomial. This was the main theorem proved last time. So the Galois extension K over F arises as a splitting field of some polynomial in Fx. So there is some polynomial Fx in capital Fx with K the splitting field of F. Okay, but since L contains F, we may view Fx as a polynomial over L, i.e. as an element I should say, sorry. It's always a splitting field of a separable polynomial. So F is separable. Yeah. And then we may view Fx as a polynomial over L, i.e. as an element of Lx. And, well, K is the splitting field of F. So then K is the splitting field of some polynomial in Lx, if I view Fx as a polynomial of Lx. Some separable polynomial Fx, which I'm viewing as an element of Lx. And then, well, a particular case of the theorem proved last time tells us that the Galois extension K over L is, the field extension K over L is Galois. So since K can be viewed as a splitting field of some polynomial over L, then this implies that K is a Galois extension over L. Okay, so we had as input that K was Galois over F, but then using the criterion that a field extension is Galois if and only if it's a splitting field of some polynomial, it's more or less immediate that K is in fact Galois over L, which is what we just proved. Okay. But since K over L is Galois, well, by another one of the criterions for Galois extensions, this tells you that L is precisely the fixed field of the field extension. So since K over L is Galois, L is the fixed field. Sorry. Well, let me write it out. So L is the fixed field. I can write it in my symbol. So L is the fixed field of the Galois group. Equals fixed field of let's say what here. Okay, because one of the criteria for being a Galois extension is that the base field is the fixed field of the automorphisms of the extension. Okay, but then we're done because the Galois group K over L certainly a subgroup of Gal K over F, because if some field extension fixes L, then it certainly fixes F, which is a subfield of L. So it's a subgroup, and then L, which is K to the Gal K over L, is phi applied to the Galois group of K over L. So phi is indeed surjective. This is what we had to show. We had to show that L could arise by taking the fixed field of some subgroup. Okay, so we've now shown that phi is injective and surjective, therefore it's bijective. And to show its inclusion reversing, well, this is immediate from the definitions. So suppose that H1 is a subgroup of H2 in the Galois group. Let V be in the fixed field of H2. This means that for any H in H2, H fixes V. But since H1 is a subgroup of H2, all elements of H1 are also in H2, so I can apply this to see that V is fixed by all elements of H1 because they all lie in H2. So since H1 is a subgroup of H2, in particular we have that, so we have in particular that H1 fixes V, i.e. V is in the subfield of all elements fixed by H1, i.e. K, H2. So we've just shown that every element that's fixed by H2 is also fixed by H1, so the fixed field of H2 is a subfield of the fixed field of H1, as required. Okay, so it's basically obvious from the definitions, or immediate from the definitions, once you write it out what they mean, that phi is inclusion reversing, and smaller groups correspond to bigger fields. Okay. So let me just write down for the future that we saw in the proof. That K over F Galois implies K over L Galois for L, an intermediary field. Okay, further. The inverse of phi we see from the proof is the map phi inverse taking intermediary fields to subgroups and the way the inverse works is that we take an intermediary field to the Galois group of K over L. Okay, so that's the inverse to phi, and that's shown in the proof above. Okay, so here's another question, right? If we take some intermediary field, then we know that K is Galois over L, but we don't know that whether or not L is Galois over F. Okay, so question. given an intermediary field L, when is L Galois over F? Okay, and this is answered by the following theorem, which is going to be the last theorem of this course, and it's also a fairly important theorem in its own right. So if we have a Galois extension, then I'd like to formulate a criterion. So by the fundamental theorem of Galois theory, for any intermediary field, the study of intermediary fields is equivalent to the study of subgroups. So we'd like to have some criterion for intermediary fields giving us Galois extensions of F in terms of group theory, and that's what the following theorem provides. It says that an intermediary field L is Galois over F if and only if the corresponding group, which is Gal K over L, is normal in the full Galois group. So an intermediate field L is Galois over F if and only if Gal K over L is a normal subgroup of Gal K over F. Proof. Okay, so let's just recall the definitions. L is Galois over F. So we have various different criteria for when L is Galois over F. In this proof, we're going to use the original criterion. So L is Galois over F if and only if the number of automorphisms of L over F is the degree of the field extension of L over F. Okay, so we start with a simple claim. Namely, we claim that every automorphism of L over F can be extended to some automorphism of the bigger field K over F. So every automorphism in L over F can be extended to some automorphism of K over F. Or in other words, that if I have some element sigma in automorphisms of K, which such that if I restrict it to L, I get tau. Okay. Proof. So this again follows using the criteria from the last lecture. So we know that Galois field extensions arise as splitting fields. Okay, so the Galois extension K over F is the splitting field of some separable polynomial with coefficients in F. Okay, but now we can just apply directly the theorem on extending isomorphisms to splitting fields. So we proved the theorem, remember, saying that whenever we have an isomorphism, and we have some polynomial in the fields, then we get correspondingly an isomorphism between the splitting field of the polynomial. So we can apply, so K is a splitting field of some separable polynomial. Then we can apply directly the theorem on extending isomorphisms to splitting fields, which is proven in the past lectures. To just extend the isomorphism tau to the splitting field K. Okay, so we just literally apply the theorem directly, and it tells us that starting with this isomorphism tau from L to L, I can extend it to the splitting field of the polynomial. So of the splitting field of the polynomial fx to get some isomorphism from K to K. Okay, so of course I can view and tau is the identity on F, therefore sigma is the identity on F. And so here, right, we are viewing Fx as an element of Lx. As in the previous proof, I can view the polynomial fx in fx as a special case of a polynomial with coefficients in L. Because of the coefficients lie in F, they also lie in L. And then I can directly apply the theorem on extending isomorphisms over a base field to isomorphisms over a splitting field. Since K is a splitting field of some polynomial with coefficients in L, I just immediately get what I want. Okay, so this is proof of claim of the whole theorem. Okay, so what we now have seen is that every element in the group of automorphisms of L over F can be extended to an automorphism of K. Okay, so now let H be the subgroup of the Galois group of the Galois extension K over F, defined as the subgroup of those elements which take the subfield L to L. So let's define H as the subgroup of elements sigma in gal K over F such that the image of L, of the subfield L, equals L. Okay, this notation here denotes, I should use, so let's write it like this. So this is the image of sigma. Okay, so it's the subgroup of elements such that the image of the automorphism applied to L, should be consistent. So let's write it as either the image of sigma restricted to L we can write it like this equals L. Okay, so it's the subgroup of elements sigma in the Galois group such that the image of L equals L. Okay. So it's all those elements which take elements in L to elements in L, rather than, as opposed to elements which move, as opposed to automorphisms which move elements of the subfield L outside of L. They leave all the elements of L inside L. Okay, so obviously the Galois group of K over L is a subgroup of H because elements sigma in the Galois group of L, they act as the identity on L, and therefore they preserve L. On L, therefore the image of L for these elements is just L because sigma even acts as the identity on L. But H can be much bigger. H consists of all of those elements which induce an automorphism when restricted to L. But that automorphism need not be the identity. So the Galois group K over L is a subgroup of H consisting of those elements which induce the identity on L, as opposed to a different automorphism. Okay. So from the claim, we know that every element in the Galois group of, from the claim we know that every automorphism of L, so let's go back to the claim, we know that every automorphism of L can be extended to an automorphism of K, fixing F. Okay, and such extensions give us automorphisms of L, so they in particular have to fix L. So from the claim, we see immediately that we have a surjective group homomorphism H surjects onto automorphisms of L over F, where some automorphism of K which acts, which fixes L, I can restrict it to L to get some automorphism of L over F. Okay, so the claim is equivalent to saying that this subgroup H surjects onto the set of automorphisms. This is the same as saying that every automorphism of L can be lifted to some automorphism of K. Okay. So let's call this, what should I call this? Let's call this, maybe phi is a bad notation. Let's call this psi. So the kernel of psi is well, what is the kernel of psi? It says elements sigma in H such that sigma restricted to L is the identity. So it's all those automorphisms which are the identity on L. In other words, it's the Galois group of K over L. So the set of elements which fix L. Okay. Charges. So, well, we see a lot. So, this gives us, for example, that the Galois group of K over L is a normal subgroup of H. Okay. So, now using group theory, right, using the first isomorphism theorem for group theory, since the kernel of psi is Galois of H, we have that the number of automorphisms in L of F, well, this finite group is the same as the group by the first isomorphism theorem from group theory, H quotiented by the kernel so it's the number of elements in H quotiented by gal k over L, since that's the kernel, is H. So the number of elements in the number of automorphisms of L over F equals the number of elements in this subgroup H divided by K over L, because the number of elements in the Galois group is K over L, is the degree of K over L. Okay, but H is a subgroup of the Galois group of K over F. So the number of elements is less than or equal to the number of elements in the Galois group, which is the degree of K over F. So then, right, we see that the number of elements is always less than or equal to K over F divided by K over L equals, so by the Tower theorem, K over F is K over L times L over F. And further, equality occurs if and only if this inequality, number of elements in H equals a Galois group, is an equality, which is the same thing as saying that the subgroup H is everything. So we have this equality between the number of elements in the automorphism group of L over F and the degree of L over F, if and only if H is the entire Galois group. So i.e., so since the equality is equivalent to L being Galois over F, we see now that L is Galois over F if and only if H is the entire Galois group, i.e. if and only if sigma L equals L for all sigma in Gal K of F. And so what we need to show for the theorem is that H equals the Galois group if and only if, remember the criterion of the theorem, if you go all the way back to the statement, it said that L is Galois over F if and only if the group Gal K over L is normal in Gal K over F. So what we need to prove is, so now we know that it's Galois if and only if H equals the entire Galois group. So we need to prove that this criterion, H equals the Galois group of K over F, occurs if and only if Gal K over L is normal in Gal K over F. Okay, so one direction is easy. So we saw above that the Galois group was a kernel of some group homomorphism, and well, the kernel of a group homomorphism is always normal. This is one of the definitions of normal subgroups. A group is normal if and only if it occurs as a kernel of some group homomorphism. So the Galois group is definitely normal in H. So the Galois group is definitely normal in H, and then if H is a Galois group, it's going to be normal in the whole Galois group. So it's certainly true that if H equals Gal K over F, this certainly implies that the Galois group is normal in Gal K over F. Okay, and it only remains to prove the reverse direction. So suppose that the Galois group of K over L is normal in the Galois group of K over F. We need to prove that H is the entire Galois group. So we need to prove that under this assumption, sigma L equals L for all sigma in the Galois group of K over F, the biggest Galois group. Okay, so let L be an L, sigma be in the Galois group. Then we claim that sigma, I would like to prove that sigma L equals L. The first thing to prove is that sigma L is a subset of L. So I claim that sigma takes any element L, little l in big L, to some other element in the intermediary field L. Okay, so here's the claim, and I have to use that the Galois group K over L is a subgroup of the big Galois group. So let's use here that L is the fixed field of the Galois group of K over L, since K is a Galois extension of L. So since L is a fixed field of this, it's of Gal K over L, it suffices to show that for any tau in the Galois group of K over L, that tau fixes, so it suffices to show that for any tau in the Galois group, that tau fixes sigma L, because the fixed field, because every element fixed by all the elements in the Galois group, the set of the fixed field is precisely L. So if it's fixed by all elements in the Galois group K over L, it must lie in L. Okay. We have to use the assumption somewhere, and we now use that the Galois group is a normal subgroup of Gal K over F. So since gal K over L is a normal subgroup of gal K over F, well, this is the same as saying that sigma, that if I conjugate any element in the Galois group by sigma, or by any element in fact, from gal K over F, it will just fix, I will remain in the subgroup. So a subgroup is normal if and only if under conjugation, the conjugation action fixes the group. Okay, so it's this statement. If I conjugate by the element sigma, then it fixes the group K over L. So since it's normal, we have this. So there exists some element G in the Galois group K over L with sigma G sigma inverse equals tau. And now I plug this back in. Then, so let's call this equation 1. And then equation 1 will give us that sigma G sigma inverse, I now plug this in as a replacement for tau of, sorry, this is not equation 1, this is what we're trying to prove, but so I should write it like this, then tau of sigma L, yeah, let's still call this 1, equals, replacing tau with sigma G sigma inverse, then this cancels, it can be sigma G of L, but G is in the Galois group of K over L, so G fixes L, so this is sigma L, and we've proven 1. So this is what we wanted to prove. So we've now shown that, so we've now shown 1, and by the above, this completes the claim that sigma L lies in L. Okay. So for any L in L, any sigma in the Galois group for K over F, we have that sigma L is in L, i.e. sigma takes, i.e. the image of the intermediate field L lies in L. But now, since sigma is an automorphism, then we have that the degree of L over F equals the degree of sigma L over F, since it's an automorphism. Okay, but now the degree of L over sigma L, viewing sigma L as a subfield of L as above, this equals the degree of L over F divided by the degree of sigma L over F, but we just proved from equation 2 that these two quantities are the same. So the degree, so sigma, so we've shown that for any sigma in the Galois group of K over F, sigma L is a subfield of L, but further, the degree of the extension L over sigma L is 1. So this implies that we in fact have that sigma L equals L, and this by definition is the same as saying that sigma lies in the subgroup H of those elements such which take L to L. So this implies that H equals the entire big Galois group. Okay, and this was what we had to prove. We had to prove that H equals that if the Galois group of K over L is normal in the Galois group of K over F, then H equals the big Galois group, and this completes the proof. Okay, so that's the end of the course, and thanks a lot for attending this course. I hope that you learned something. I have office hours tomorrow. I'm going to hold them at the time I sent you. So if you have any last minute questions about the exam, please come to the virtual office hours tomorrow. And also, don't forget to fill out the course evaluations. They're very important to the department, and we do take them seriously. Okay, so thanks a lot.